Hello and welcome to this fourth data collection and pre-processing lecture in this course Master in Artificial Intelligence. So we will continue to talk about how to gather relevant data from various sources, ensure its quality and pre-process it to make this data suitable for analysis and modeling in this lecture also. So let's look at now image feature extraction algorithms. We have looked at the text and feature extraction algorithms in the last couple of lectures. The image feature extraction algorithms play a crucial role, a critical role in computer vision tasks, particularly. And they do so by capturing relevant information from images in a form suitable for analysis and interpretation. So that's the whole thing happens. Now, what are such key image feature extraction algorithms? Let's take a look at that. The histogram of oriented gradients (HOG) is a popular technique for object detection and recognition, as you can see here. It calculates the distribution of gradient orientations in the local image regions, capturing the shape and texture information of the objects. You can see that very well here. HOG features are often used in pedestrian detection, face recognition, and object detection tasks. So that's all about HOG for the time being. Then another one is SIFT, Scale Invariant Feature Transform. Now, it's a feature detection and description algorithm that identify key points in an image regardless of scale, rotation, or illumination changes. It extracts distinctive local features based on the image gradients and generate descriptors representing the appearance of these key points. SIFT features are widely used in image matching, object recognition, and panorama stitching. Right. The third one that you need to know is the speeded up robust feature SURF. It's similar to SIFT but computationally very efficient, much more efficient. It detects feature points using box filters and approximates the gradient information using integral images. Some features are robust to changes in scale and rotation and are used in applications like object recognition, image stitching, and video tracking. Then there is, we talked about this CNN, convolutional neural network. They have revolutionized the image feature extraction by automatically learning hierarchical representation of images through convolutional layers. CNNs learn to extract features at different level of abstraction, from low level edges to textures to high level object parts and semantic concepts. Pre-trained CNN models like VGG, ResNet, and MobileNet are often used as feature extractors or fine-tuned for uh, specific image analysis tasks. Low binary pattern LBP is another one. It's a texture descriptor that characterizes the local texture patterns on a grayscale images. It compares the intensity of each pixel with its neighboring pixel and encodes the result into a binary pattern, as you see here. LBP features are used in texture classification, face recognition, and material classification tasks. Then there are histogram-based descriptors such as color histogram, texture histogram, and shape histograms. They capture statistical distribution of the pixel values, textures, or shapes in images. And these descriptors provide compact representations of image content and are used in various image analysis tasks, including image retrieval, object recognition, and content-based image retrieval. Then there is another type of image feature extracting or extraction algorithms like edge detection algorithms such as Canny edge detector, Sobel operator, or Prewitt operator, which identify edges or boundaries in images for detecting abrupt changes in pixel intensity. Edge features are useful for image segmentation, object detection, and shape analysis tasks. The last one that we want to talk about as image feature extraction algorithms is corner detection algorithms such as Harris corner detector or Shy-Thomas corner detector, which identify corner points in images based on the local intensity variations. The corner features are used in applications like image stitching, camera calibration, and object tracking. So these are some of the key image feature extraction algorithms based and used in computer vision tasks. The choice of algorithm obviously depends on the specific requirements of the task, including the nature of the images, the desired level of abstraction, computational efficiency, and accuracy constraints. Having looked at how to extract features, then you need to explore the pre-process data, then you to gain insights into its distribution, relationship, and patterns as you see here. And then you need to explore data by visualization techniques such as histograms, scatter plots, heat maps, and box plots, which can be used to explore the data visually. So visual exploration is important. The last thing that you do in data collection, analysis, and pre-processing, you split the pre-processed data into training, validation, and testing sets for model training, evaluation, and validation purposes. Typical split ratios are 60 to 80% for training, 10 to 20% for validation, and 10 to 20% for testing. And it depends on the size of the data set and specific requirements of the project. So by following these steps, you can gather relevant data from various sources as you saw, ensure its quality and pre-process it to make it suitable for analysis and modeling. And that lays the foundation for your data-driven projects. So having looked at how to collect and pre-process data, we will now in next two lectures take a look at an example of how actually these methodologies were used to collect and pre-process data so that you get a good idea of how it happens in real life. So thank you so much for watching this fourth data collection and pre-processing lecture. I hope you're continuing to learn new things, continuing to enjoy. And I do look forward to see you again in the next lecture. Please feel free to message me if you have any question. I'll be happy to answer a question. It's also download the PDF file to take a look at anything at a closer hand.